Good afternoon. My name is Bruno Klaus, and I'm here to present the solution of our group, the Team Paraná, ch- which was the first place solution on the public leaderboard for the KDD BR competition of 2021. So about us, the name of our group is Paraná. It stands for Pattern Recognition and Network Analysis. This is a research group within the Federal University of São Paulo, more specifically the Institute of Science and Technology located in the city of São José dos Campos. So Paraná has quite a few members, but three of us were part of this competition. So me, Bruno Klaus, currently a PhD candidate. We have Jessica, also a PhD student and a data scientist at Blue 365. And lastly, William De Hunster, who is a data scientist at Serasa Experian Data Lab and currently a master's student at the Federal University of São Paulo. So let us introduce our problem. So Travelling Salesman Problem was proposed by Manga in 1932. It is one of the most studied problems in operations research and combinatorial optimization. And it is known to be a very hard combinatorial problem. In fact, it is NP complete. So what is the task at hand here? Well, it's quite simple. If we are given a list of cities, then we must find the route that goes through all the cities, returns to the origin, and among those, it must be the one that has the shortest total distance covered. And of course, the Travelling Salesman Problem has quite a few applications. For example, the delivery route. So you can ask what is the best route to deliver the orders. Warehouse order picking. You can ask what is the best order to collect the items from multiple purchase orders. And also scheduling. So what is the best way to meet all commitments? And also, there are several ways to try to solve the problem. For example, with brute force, you can simply enumerate all possible solutions, try one by hand. So obviously, you eventually find the solution, but it is really, really expensive. It takes too long, and it is considered to be impractical for a problem with more than just a handful of instances. Again, we can also use heuristics, and then there's a whole variety of heuristics, such as genetic algorithms, greedy algorithms. They can offer some bang for your buck. Some performance boosts, but they're way quicker than the brute force solution, but they won't always return the optimal solution. And another approach which can substitute those sorts of heuristics is, well, let the data decide instead of your own personal heuristic that you try to manually find by yourself. Just use the data, and then we can use the machine learning approach to try to find on its own the sorts of patterns within the data that can help us guide solutions for the traveling salesman problem. What if we use machine learning to predict whether there is an edge between one node and another node in the optimal TSP solution? In other words, what we are trying to do here is what we call link prediction. So in some cases, there might be an edge from here. You see in the image from A to B in the optimal solution. We must predict that it does exist, or maybe it doesn't exist. Then we can use that information later on, which is not the focus of this competition, to actually form the optimal solution. Another interesting thing is that because it is a kind of a sparse problem, there's some class imbalance because most of the edges will not be part of the solution. So that is something that does shape our problem. About data and pre-processing, here you can see the TSP solution. So in total, our data set had 100K, that is 100,000 training examples with 50 to 200 city nodes. And then the test set was way smaller than that. It was just 2,000 samples. And each example consists of coordinates of the traveling salesman problem instance. So you have X and Y, which are the coordinates of the nodes. And you also have an attribute M, which serves as a Boolean mask for node I, indicating if it belongs to the instance or not. So you can essentially get the number from 50 to 200 using this attribute M. And lastly, the target is an adjacency matrix of the optimal solution. So to work better with our model, we had to transform the dataset into the PyTorch format. And that is partly because we have some really useful graph neural network libraries in PyTorch, such as the PyTorch geometric. Then for modeling, we create a KNN graph with k equals 20. Each city node will be connected by edges with another 20 cities. Another thing that I will mention here is that we also converted the initial CSV file, which was it basically stored the target as dense matrices. And that was very suboptimal for, with respect to the size. So what we do is kind of on demand. When we read the batches, the main batches, then we convert from sort of a list of non-zero indexes to an actual dense matrix. So that is way better than what was originally the problem for the amount of space used. About modeling, what we tried to do was we searched for a few convolutions. So in the end, we chose the graph, an appropriate graph convolution to perform a differentiable message passing through the graph. We ended up choosing the edge convolution. So if a given node I has features denoted by xi, and the neighborhood it's denoted by n of I, we calculate the updated representation with this following formula. So as you can see, one very interesting thing about this convolution is that not only you have the xi, but you also have node differences, which is pretty interesting, and it's a nice thing to have, especially because Travelling Salesman Problem is something that is invariant to translation. So we wanted to explore this sort of a fine space of just subtracting the coordinates from one node to the other. And here you can see this age letter here. This just denotes that you use some multi-layer perceptron to classify after each of these convolutions, you use this multi-layer perceptron to propagate further. You could use any differentiable architecture. We used a multi-layer perceptron for that. And another very important thing, as I mentioned, the data is unbalanced. So we had to use a weighting scheme, which was proposed previously, but it's really essential to our work because any nodes that are part of the TSP solution will have a weight W1, whereas the rest are assigned a weight W0. So we have the information actually of how many edges will be part of the TSP solution. So we can use sort of the inverse of that. We can just calculate the proportions according to the information, and then we can counteract the unbalancing of the classes. So by choosing an appropriate weight for both classes, the class that one that identifies if an edge does exist, and 0 if it does not exist, and then we can make up for the unbalanced data. Okay. What else? Okay, so we stacked a total of 5 edge convolution on layers. Now that I think of it, maybe a bit overkill, but but it worked. So it was followed by a multi-layer perceptron MLP with 2 hidden layers. And the differentiable model age that I mentioned before, age of data of each convolutional layer is a multi-layer perceptron with a single hidden layer of size 128. And Adam was used to optimize the model, so the learning rate we chose was simply 0.01. All right, so again, summarizing, we have a model, a GNN, a graph neural network with stacked edge convolution operators, and a loss function addressing the unbalanced classes. And for the evaluation was the evaluation of the challenge. We used the F1 score on the optimal adjacency matrix and the predicted adjacency matrix. That is, the score they used in the leaderboard. But also the loss. Aside from that, we also had that loss function I mentioned before, just sort of a squared error, but with appropriate weighting. Right. So finally, we get on to the results. Of course, we are currently first on the Kaggle leaderboard with a little bit of a gap in hand. Of course, anything could change, but yeah, that's how it is right now. And here you can see the local validation. If you plot the loss function by epochs, you can see that it converges sort of quickly. Here you can see, for example, the F1 score starts after the first epoch at 10.11, near 11, no, so like 10.9 more or less for validation, and then it reaches something like 11.2, 11.34, and it sort of converges after just a few epochs. So that's why we don't show the graphic, the plot much further than that. And the result of the test public leaderboard was 0.10645. So that was the final result. Public leaderboard a little bit lower than the validation score. Nonetheless, still pretty decent score. Good enough to surpass the greedy baseline and the other competitors on the public leaderboard, at least, without using many submissions at all. So in the end, we developed a model to predict links between edges that can aid solve. It can aid solutions of the traveling salesman problem. It was enough to reach first place in the public leaderboard and overcome the greedy approach. To do that, we used GNN with stacked edge convolution operators and a loss function addressing the unbalanced classes. And you can see here our references. Those are our references, and that is all. Thank you very much. If you have any questions, so please let me know.